Hello and welcome to a new lecture in which we will do an example. So let's consider a simply supported beam. So this beam will be supported by a pin at A and a roller at B. And it's acted upon by a force that has a magnitude of 100 kilonewtons, and it's oriented at 45 degrees at point C. The total span of the beam is 10 meters, with distance AC being 6 meters and distance BC being 4 meters, of course. What we need to do is draw the internal force diagrams for this beam, so hence the axial force, shear force, and bending moment diagrams. You should know that whenever there are forces that have components directed along the beam, then probably there will be an axial force internal to the beam, so then you'd have to draw that diagram as well. Having said that, let's draw a free body diagram of the entire beam, in which we will replace the supports with corresponding reaction forces. And also I've resolved the force, the 100 kilonewton force, into its components. So a vertical component and a horizontal component of magnitude 70.7 kilonewtons each. So let's proceed to solve for the reaction forces. Very quickly, sum of the forces along X will give us the reaction force at AX equals to 70.7 kilonewtons going to the right. And then if we sum the moments at B, we can then solve for the reaction force at AAY, the vertical reaction force at A, and that will be equal to 28.3 kilonewtons going upwards. Then, in a similar fashion, we can sum the moments at point A and solve for By, the vertical reaction at B. And I'm using moment equations because, as you know, with moment equations you can eliminate other unknowns and other forces that you don't need, and your equations will be simplified. So now By resulted as equal to 42.4 kilonewtons going upwards. The question is are these reactions correct? This is a very important question, because if the reaction forces are not correct, everything forward from now on will be wrong. So I can sum the forces on the y direction, and hence my equilibrium is correct. So my reaction forces are correct, which means I'm okay to proceed. So always perform this check. Make sure that your reaction forces are always correct, because as I mentioned, everything that you will do will be wrong. Very, very important to perform that check. Now, let me draw again the free body diagram of the beam, and I will replace the reaction forces with their actual values. As you can see, and the span, because we need that if we have to sum moments, for example, 6 meters, 4 meters. And firstly, we need to see what's happening to the left of the force. So we will proceed by cutting the beam just to the left of point C of the applied force. After doing that, I will analyze the equilibrium of the left-hand side free body diagram. So we only have to draw that one, like so. So the internal forces that I will always draw with their positive direction. So shear force going downwards on the left-hand side of the free body diagram, bending moment rotating counterclockwise, axial force pulling out from the beam. Some of the forces on the horizontal direction will solve us for the axial force at C on the left-hand side of P, negative 70.7 kilonewtons. That indicates that member AC is in compression. Some of the forces in the vertical direction then will solve us for the shear force at C on the left-hand side of the applied force. So that's positive 28.3 kilonewtons going down on the left-hand side free body diagram. And some of the moments at point C equals 0 will solve us for the moment at C on the left-hand side of the force equal to plus 169.8 kilonewton meters, rotating counterclockwise. So the bending moment is positive. Now, you can sum the moments about any point you wish, but if you sum the moments about the cut, then in theory you don't really need to know the shear force at that location, because the shear force goes through that point and you will eliminate it from your equation anyway. Then we do the same thing. We cut the beam, but to the right of C, of the point of the application of the force. We'll have to draw again the free body diagram, and I will use again the left-hand side of the free body diagram. Everything will be the same when I draw this free body diagram as in the previous case, except that now the free body diagram captures the force as well. So the two 70.7 kilonewton force components, horizontal and vertical force components. But then everything else is the same. And of course the notation indicates now that the internal forces are calculated at the right of C. So again, we will write the same equations, sum of the forces in the horizontal direction, in order to solve for the axial force in the beam between BC. So that would be 0 kilonewtons, no more axial force in segment BC of the beam. Then we can sum the forces in the vertical direction to calculate the shear force at point C, but to the right of the force. So VC to the right of the force is now negative 42.4 kilonewtons going upwards. So that indicates that discontinuity in the shear force that must be equal in total to the magnitude of the applied force, 70.7 kilonewtons. And finally, summing the moments at the cut location will solve us for the moment at point C on the right side of C of the applied force, plus 169.8 kilonewton meters, rotating counterclockwise on the left-hand side of the free body diagram. So we now know the values, and we know from the previous example that we've solved in the lecture before that we expect that the shear force diagram will be constant between the application of the concentrated forces, and the bending moment will be linear between those points. All we have to do now is draw the diagrams by using the forces, the values that we just calculated. The easiest one to draw is the axial force diagram. So segment AC of the beam is in compression with a magnitude of 70.7 kilonewtons. It's this part that I'm hatching right now. And section BC of the beam has no axial force, 0. So that's the diagram of the axial force. Always indicate the units of the numbers that you're writing on the diagram, as well as which side is tension and which side is compression. The shear force diagram, jumping up by 28.3 kilonewtons at A, constant from A to C, jumping down by 70.7 kilonewtons at C to a negative 42.4 kilonewtons, and then being constant to point B, and then jumping up by 42.4 kilonewtons at B and ending up at 0. So that's the shear force diagram. Don't forget about the units and also those symbols indicating positive shear and negative shear. Finally, the bending moment diagram has values of 0 at A and B because the beam is free to rotate at those points, being supported on a pin and a roller, and the maximum magnitude at C of 169.8 kilonewton meters. We need to write those units as well, kilonewton meters, and also, as for the other diagrams, indicate the signs and the behavior of the beam. Now, one important thing that you need to know is that the shape of the bending moment diagram roughly, very roughly, indicates the inverted deflected shape of the beam. So if you look at the beam, points A and point B cannot move vertically because of the support, but that force is pushing downwards at C. So the beam would likely deflect as indicated by the green dashed line, which again, if you look, roughly is reflected by the shape of the bending moment diagram, not exactly, very roughly, and of course with a change in sign. So the bending moment diagram is flipped over. Thank you very much for watching this example, and I will see you again at the next lecture.